Welcome to the High Voltage AI podcast. It's Wednesday, and we're continuing our week-long deep dive for electric utility engineers, drawing insights from the High Voltage AI newsletter on Substack. This week is all about the massive shifts in power systems. Today, specifically, we're tackling system integration challenges, protection, coordination, and grid codes. So the core problem we're digging into, and it's foundational for the grid's future, is how these grid-forming inverters are changing everything, how power grids operate. And this isn't just a minor adjustment, it's a major challenge for our existing protection systems. The stakes are incredibly high. Get it wrong, and reliability, the thing we all count on, gets compromised. But get it right, and we enable that reliable, renewable energy future we really need.
Exactly. And our mission today is really to understand why. Why are those traditional protection schemes kind of falling short in some situations? We need to explore the really complex coordination challenges engineers are facing, and more importantly, how they're solving them. How do we make this renewable transition not just possible, but, safe and reliable?
Right. And to really hit home just how big this shift is, let's start with a real-world story, the Duke Energy case. So Duke Energy, they commissioned their first grid-forming battery storage system in North Carolina. And their protection engineers found something, well, unsettling. Their standard time-current coordination, stuff perfected over decades, it just didn't work right. That relatively low fault current, maybe 1.5 per unit from the grid-forming inverters, it wasn't enough. It wasn't enough to operate the backup protection devices fast enough. It created these blind spots, compromising reliability, and just quickly, per unit, that's just a standard way we normalize electrical values to compare systems easily. And the fix, it wasn't quick and it wasn't cheap. We're talking 6 months. $2 million in protection system upgrades.
Wow.
They had to implement communication-assisted protection, adaptive relay settings, better monitoring. But the key thing is they developed a replicable approach, something the whole industry is now looking at.
Yeah, that Duke story really highlights it. This is probably one of the most complex engineering problems utilities are grappling with today. You're trying to maintain those super high reliability and protection standards, which customers absolutely expect, while fundamentally changing how the grid actually operates. It's a real balancing act. Innovation versus rock-solid reliability.
Okay, so let's unpack that. We built our protection philosophy on certain ideas. What were those traditional assumptions that are now being so fundamentally challenged?
Well, traditionally, everything was built around synchronous generators. Think big spinning machines. We call it the high fault current paradigm. During a fault, these machines pump out massive current, 5 to 10 per unit maybe, for several cycles. Their behavior is predictable. We understand how the current decays. And critically, it's directional. Clear flow from the generator to the fault. And they sustain that current until a breaker trips. So naturally, our protection coordination relied on that. Overcurrent protection needs high current for speed and selectivity. Time grading for backup assumes enough current is there to eventually trip the backup device. Distance protection, impedance-based. It expects certain high current levels to see the fault correctly. Even differential protection, which is sensitive, is designed around predictable changes in that high fault current.
Okay, so if I'm an engineer, spent my career relying on those big predictable currents, what's the biggest thing I need to unlearn with inverters? Is it just the lower current, or is their behavior fundamentally different during a fault?
That's a great question. Because the grid-forming inverter reality is totally different. It's not just lower magnitude, it's a different control philosophy. Synchronous generators react with huge current. Grid-forming inverters provide a controlled current, much lower, maybe 1.2 to 2.0 per unit max. And they limit it fast, like 1 or 2 cycles fast, to protect their own internal semiconductors.
Self-protection.
Exactly. And their response is programmable. You can adjust the fault current magnitude and duration. Plus, here's a big one, bidirectional capability. They can source or sink current. That completely upends the old one-way flow assumption. And the protection implications are direct. Lower current means reduced sensitivity for old relays. They might just not see the fault.
Right. They don't trip.
Exactly. Huge coordination challenges because our time current curves are all wrong for these low levels. Distance relays, they have reach problems. They can't accurately see the fault through the inverter's impedance sometimes. And that bidirectional flow, it messes up traditional directional schemes big time.
Okay, so understanding this new reality, how does it change how we even analyze fault currents? Let's get into those current limitation mechanisms. They sound critical.
Oh, they absolutely are. Inverters have these sophisticated mechanisms mainly to protect their own power electronics. The IGBTs, those high-power switches, they're sensitive. Conceptually, the max fault current is always the lowest of several internal limits. It could be thermal limits, switching speed limits, or a programmed limit set for protection coordination.
So it's designed to cap the current intentionally.
Precisely. It protects itself first. If the measured current goes over a threshold, it quickly reduces its output. But importantly, it tries to maintain grid-forming operation and coordinate with protection. It's an intelligent response, not just a simple trip. And we also have to consider fault current versus system strength, how strong or weak the grid is. Under strong grid conditions, high short-circuit ratio, SCR, say above 3.0, the grid itself provides a lot of fault current.
Right, the traditional sources dominate.
Yeah, the system voltage holds up better, and traditional protection might still work okay. But under weak grid conditions, SCR less than 2.0 maybe, the inverter becomes the main source of fault current. And here, the system voltage can actually collapse, which limits the inverter's output even more.
So it gets worse in weak grids.
Exactly. That's where alternative protection schemes become absolutely essential, not just nice to have. The available fault current is really a complex interaction of system voltage, impedance, inverter limits, and its control response. Very interconnected.
That's a crucial point. So if the currents lower in grid conditions matter so much, what are these enhanced protection strategies? How are we actually overcoming these challenges?
Well, one of the biggest shifts, and really essential for the future, is communication-assisted protection. We're moving beyond just local measurements. Modern schemes rely heavily on high-speed communication. Think line differential, using fiber optics for super-fast end-to-end protection. We're seeing enhanced bus differential, transformer differential, much more sensitive, which you need for these lower fault currents, and distributed protection for those complex setups with multiple inverters. We're also using things like transfer trip schemes that detect a fault locally, use communication to trip remote breakers, coordinate the whole thing. And permissive and blocking schemes are evolving too, like permissive overreach transfer trip, directional comparison, even current reversal detection to handle that bidirectional flow. Then there's adaptive protection systems. Think relays with multiple setting groups.
Like different modes.
Exactly. A relay could switch settings based on whether the grid is mostly traditional generators, high inertia, mostly inverters, low inertia, mixed, or even in an emergency restoration state. The key is real-time adaptation. Settings change based on system inertia, actual available fault current, grid forming capacity. So, for example, if grid-forming resources make up more than, say, 60% of the capacity in an area, the system might automatically lower overcurrent pickups, enable communication schemes, activate voltage protection. It's dynamic.
Wow, a living protection scheme.
Sort of, yeah. And finally, voltage-based protection is becoming more important. Enhancing under-voltage protection, tripping, based not just on low voltage, but how long it stays low or how fast it drops, rate of change.
Okay.
Over-voltage coordination is also key. Inverters can sometimes cause voltage rise if load suddenly drops, so they need to coordinate to reduce their voltage reference, keep things stable, and frequency-based protection is getting enhanced too, coordinating with synthetic inertia and applying rate of change limits if frequency deviates too quickly.
This all naturally leads to the rules changing. What new technical requirements, new grid codes are emerging? Because the old rule book clearly doesn't fit anymore.
Precisely. We're seeing major updates globally. Here in the U.S., a big one is the NERC standard PRC 0291 coming in 2024. It sets comprehensive protection requirements just for inverter-based resources. Mandates minimum sustained fault current, better ride-through for voltage and frequency dips, coordination requirements, continuous monitoring. It's a landmark standard.
Okay, that sounds substantial.
It is. And then there's FERC Order 901 from 2023. That focuses on the grid forming capability itself. Things like continuous voltage regulation, primary frequency response, ride-through, even harmonic limits for power quality. And beyond national standards, you see interesting regional differences.
Right, because grids aren't all the same.
Exactly. Look at ERCOT in Texas. They mandate synthetic inertia for resources over 10 megawatts, need fast frequent response like within half a second, dynamic reactive power, even grid forming for black start.
Black start capability, wow.
Yeah, critical for resilience. Then CAISO in California requires grid forming for new battery storage over 20 megawatts, needs at least 1.2 per unit fault current for 10 cycles, mandates coordination studies, field testing. Over in PJM, they have sub-second frequency response needs, continuous voltage regulation at the interconnection point, enhanced studies, specific performance for ancillary services. Each region is tailoring things.
That level of detail really shows the complexity. What's fascinating is how advanced monitoring and control systems become absolutely essential here. It's like giving the grid new eyes and a much smarter brain.
That eyes and brain analogy is perfect. Phasor measurement units, PMUs, are really leading the charge for these wide area monitoring systems. They give us incredibly high-resolution data, 120 samples per second, unprecedented visibility across the system of how these grid-forming resources are performing in real time.
So you can see dynamic events much more clearly.
Absolutely. Huge for analyzing disturbances and even for predictive analytics, using machine learning on PMU data to predict faults before they happen. You combine that PMU data with SCADA, advanced metering infrastructure, weather data. It helps optimize the whole grid state, including dynamically adjusting protection settings. On the control side, real-time control coordination is vital. Think emergency control systems. If there's a major event, the system can activate a grid-forming emergency mode, coordinate protection settings changes, maybe shed load if needed, and monitor the recovery. Automatic generation control, AGC, is also evolving. The AGC signal gets augmented by the grid-forming contribution, making the whole grid more agile.
So the controls are getting smarter too.
They have to. And the interface between protection and control is critical. Constant sharing of fault info, coordinating actions, monitoring restoration, validating that protection worked. It's a tight feedback loop.
Okay, connecting all this. How do utilities actually do this? Implement these huge changes in a structured way? It can't just be flipping a switch.
No, definitely not. Most are using a staged deployment strategy, very methodical. Phase 1 is usually pilot testing, 6 to 12 months maybe. Small-scale deployment, lots of studies, field tests, developing procedures, training.
Learning the ropes.
Yes, exactly. Phase 2, limited deployment, maybe 1 to 2 years. Expand more sites, integrate with existing systems, validate performance, ensure compliance. Then Phase 3, commercial deployment, 2 years plus. Large-scale rollout, standardized approaches, market integration, continuous optimization, sharing knowledge across the industry. It's a careful process. The whole engineering workflow changes too, especially the protection study process. 5 key steps now. First, detailed system modeling, including the dynamic inverter behavior. Second, fault analysis specifically for that limited fault current. Third, coordination studies using these new fault levels. Fourth, calculating optimized settings for all the different modes. And finally, extensive field testing to prove it works under real conditions. Plus, a detailed commissioning checklist is essential. Verify settings, test communications, check control coordination, test emergency procedures, train staff. And that training piece, training and competency development, is huge across all roles. Ops staff need to understand the fundamentals, protection changes, emergency response, comm systems. Protection engineers need deep knowledge of inverter characteristics, advanced schemes, grid codes, new tools. Maintenance folks need proficiency with the hardware, testing, calibration, comms, maintenance, safety. It's ongoing learning for everyone.
It's always great to see theory put into practice. Can you share some successful, real-world examples where utilities have navigated these challenges?
Absolutely. A great one is Pacific Gas and Electric in California. They had to integrate 300 megawatts of grid-forming battery storage. Big project. Their solution involved communication-assisted line protection with fiber, adaptive settings, PMU integration, and coordinated voltage and frequency control.
The whole toolkit.
Pretty much. And the results? 0 protection misoperation since they commissioned it. A 40% improvement in system frequency response. Successful integration enabling 60% renewable penetration. It's become a model for others in California. Another really interesting case is National Grid in New York. Integrating grid-forming inverters into a complex urban network, very tricky protection-wise. They use multi-terminal differential protection, voltage-based protection as backup, real-time adaptive settings, and integrated it with automatic switching. And the outcomes were great. Maintained protection selectivity, enhanced stability during big disturbances, even performed well during the Hurricane Sandy restoration. It's a template for other complex urban grids. So yeah, for protection engineers listening, the bottom line is pretty clear. Integrating grid-forming inverters requires a fundamental shift in philosophy. New skills are needed. We need innovative solutions that balance that rock-solid reliability with the flexibility renewables demand. It's a really pivotal time for grid engineering.
That really sums it up well. And looking at those success factors, it seems to boil down to maybe 5 key things. First, comprehensive analysis. You have to enhance studies for low-fault current, bidirectional flow, dynamic conditions.
Right.
Second, communication enhancement. Relying more on high-speed comms, less on just local data.
Absolutely critical.
Third, adaptive approaches. Protection needs to adapt in real time, not use fixed settings. Fourth, Collaborative design, protection engineers and control engineers have to work hand in glove.
Essential.
And finally, continuous learning. Technology, standards, they're moving fast. Everyone needs to keep learning. It's definitely a journey. So turning it over to you listening. What protection challenges are you seeing with inverter-based resources? Have you implemented communication-assisted protection or adaptive settings? We'd love for you to share your experiences with grid-forming integration and protection coordination.
And tune in tomorrow. We'll be looking at successful grid-forming deployments worldwide, from Australia's mandate to Texas storage projects. We'll explore what's working in practice, lessons learned. Today was about the Protection and Control Foundation. Tomorrow is about seeing how these solutions perform out there in the real world, under actual operating conditions.
If you'd like to leave feedback or have any questions, feel free to reach out to us at alex.reed.power.podcast@gmail.com.
And emma.quinn.power.podcast@gmail.com.